Welcome to Module 1. We're going to be looking at the thermophysical properties and steam tables in this video. So our goals here are that first, we want you to be able to use the language of thermodynamics properly, and then also be able to find the data necessary to solve problems from the property tables in this textbook, other textbooks, or some other resources that you might have. So what is thermodynamics? Well, it's a study of the principles of energy and how it's transformed. The first law of thermodynamics is an energy balance, and the second law of thermodynamics is an entropy imbalance. We'll write it as a balance because inequalities are distressing to an engineer, but really it's an entropy doesn't really balance in the real world. The basic terminology that we're going to need, let me just go over these fairly quickly. First of all, when we talk about a problem, we always want to start by defining a system. Basically, this means we're saying what's in and what's out. The system might be closed so that the material in there is in there at the beginning of the problem and at the end of the problem, or it might be open so that material can flow in and out, and we are defining the space and the material changes over time. A system can also be isolated. That means that not only does material stay inside, but nothing can come into our system or leave our system. Now, the way we define our system is that it's got some boundary that traps what's inside. Even if the material is flowing through, it only counts as our system when it's inside this boundary. And so the boundary is going to be very important to us because it defines exactly what's in and what's not in. And then we're also going to have the surroundings, so that's everything outside of the boundary. The two ways that we talk about problems are going to either be a control volume approach or a control mass approach. Control volume approach means I'm talking about the space itself. So this would be something like a pump where material is constantly flowing through the pump. And so in that case, I'd like to use a control volume because the space is what's important. The control mass approach follows material. So this would be something like maybe you had a marshmallow and you were going to squish it and stretch it, okay? And the shape of it's always going to change, but the material itself is what I'm trying to keep track of. So those are the two primary approaches that we use for solving most of our thermodynamics and other transport problems. Properties are very, very important. Properties are going to be any measurable characteristic of a system. So temperature, pressure, and volume are the ones that we usually use. In this textbook, V with a capital T at the top is total volume, and that's what we would normally just call volume. M is mass, N is number of moles. Density is the Greek letter rho, and that's mass per unit volume. And then you have enthalpy and internal energy. You also probably recognize the S down at the end, that's entropy. And then we have an A and a G in here, which probably are new to you, but they are other forms of energy. They are similar to enthalpy and internal energy. A is the Helmholtz energy, and G is the Gibbs energy. And we'll be talking more about those in the second half of this course. When they use V without the T at the top of it, they are meaning specific volume, which is the reciprocal of density, or it's the total volume per mass. Extensive properties depend on the extent of the system or the size of the system. So total volume, mass, and N, the number of moles, are going to depend on the size of the system. So that should be the V with the T on it. Intensive properties are the ones that are independent of size. Temperature, pressure, density, specific volume. Okay, all these variables like energy variables, entropy variables, volume variables, they actually can be either intensive or extensive. Every textbook uses a different notation, so I really recommend, instead of getting so worked up about the notation, just figure out from the units on the property whether it's extensive or intensive. If it's per kilogram, per pound mass, per mole, then that's going to be an intensive version. Okay? I'm not going to exactly use the notation from Smith and Van Ness, but I will try to put a superscript T when it's total volume, and no superscript means it's on a per mole or per mass basis. But even with that, they're not very consistent in the book. So just be really careful and always pay attention to the units. So those energy forms. Okay, again, U is internal energy. We're familiar with that one. We've seen that one for a long time. And H is enthalpy. And in the Thermo 1 course, we had it defined for us as internal energy plus pressure times volume. Okay? And we're used to working with that. We've sort of learned that internal energy is primarily used with closed systems, and enthalpy has more to do with systems with flow, that plus PV accounts for the energy associated with just moving the molecules. But there are two others. The first of these is the Helmholtz energy. Here's Mr. Helmholtz over here. A stands for Helmholtz energy, and yeah, I know there's not a letter A in there. But it's A, and it's U minus TS. Okay, sometimes you'll see it called the Helmholtz free energy. We're going to find that this one is very useful when we're trying to solve equilibrium problems where the temperature and volume are fixed. There's also a Gibbs energy. Now, you may have run into this one in a chemistry course. Gibbs energy, or Gibbs free energy, or sometimes it's called free enthalpy, is either defined as H minus TS, or since H is U plus PV, it's U plus PV minus TS. Now, here's Mr. Gibbs down here in the bottom corner. This one is going to be very useful when the temperature and pressure are fixed and I want to solve an equilibrium problem. So, turns out that Gibbs energy is a very, very commonly used form of energy. Helmholtz energy, not quite as much. Enthalpy is useful, as you've already learned, but these two other ones are going to be probably new to you. Now, states and phases. You probably first learned this when you were, maybe 3rd or 4th grade? Okay. A phase can either be solid, liquid, or gas. We have some complications like plasma and so forth, but we'll stick with the solid, liquid, and gas. Really, what we learn as we get older is that these are defined by their properties and information about exactly what condition it's in. So if I had a cup of coffee, I might describe it as being 10 ounces, want to be very specific about the volume, of liquid coffee, don't want to vaporize that coffee, at 1 atmosphere because I'm on Earth, and 180 degrees Fahrenheit. Okay, so that might be the way I would describe the state of my system. The phase would be liquid. If I include the vapor coming off of it, then I have a liquid-vapor mixture. Now, we're going to be spending more time on equations of state, but you've already been introduced to these. Any equation that relates the properties of a system, most often pressure, volume, and temperature, is going to be an equation of state. Now, it might include other energy variables also. The one you know best is the ideal gas law, PV equals nRT. Now, this would be the total volume in this case. And if I divide both sides by the moles, I get PV equals RT, which is the intensive version of volume. Okay? And in this case, R is the universal gas constant. But if I do it in a mass basis, I have to have a unit specific. And we'll talk more about that when we get to some examples with the ideal gas. Equilibrium is a very important concept for us because properties are only really defined if the system's at equilibrium. Now, there are 3 types of equilibrium. We have thermal equilibrium, which means temperature doesn't change with time. We have mechanical equilibrium, which means there's no changes in the force, which for our purposes we relate as pressure with time. So there's no change in pressure over time. And then we have thermodynamic equilibrium, which has no change in any of the properties over time. Now, reality, we don't have equilibrium ever. So we're going to aim for quasi-equilibrium. It doesn't change over the amount of time that we observe it. Okay? And we're going to call that being at equilibrium. Now, much of this course is going to be related to talking about processes and cycles. Now, a process is a change from state 1 to state 2, which is distinctly not equilibrium. Okay? Now, the thermodynamic properties are only defined for equilibrium, and I'm saying we're going to then apply them to processes. It'll be okay. We have a lot of special processes we define. The ones that I think that you want to make sure you really know the words: isothermal, constant temperature; isobaric, constant pressure; isochoric, constant volume; and adiabatic, no change in heat transfer. Okay? Now, a process could be any one of these things. If you go through several processes and eventually the system ends up back at its initial state, it's called a cycle. So a cycle is a series of processes where you end up with no net change. Okay? Now, all these various properties that we've been talking about, some are going to be independent of path. It doesn't matter how you change the volume. It's just that new volume. Okay? Others are going to depend on the path. So I know that if I am carrying heavy boxes around and I have to get boxes from here to right there, and I choose to just move the box there to there, I didn't do all that much work. But if I carry the box and I carry it out on the street around the block and come back in and get it there, the ending state is the same as my just placing the box. But the amount of work that I did, my energy levels are going to be way down because I'm just so much more exhausted. So some things depend on path, some things don't. Okay? And we're going to have one of our tests for that is that if I go through a cycle and the net change is 0, then it might be independent of path. But if the net change is not necessarily 0, it's dependent on the path that we choose. Now, I am not going to take time in this course for unit conversions. If you need help on this, please get some help now. I will provide a link to some resources for that, but let me know if you need more than that. One important thing that you should know, just kind of for the future going forward, when a problem is stated in English units, the answer needs to be given in English units. Okay? I don't really care what you do in between. You can convert everything over to CGS system. Okay? I don't care. And then convert it back at the end. Or you can work the problem in those English units or American engineering units. Okay? All I really care is that the answer needs to be in the same unit system as what was the problem statement originally. Now, a couple of special variables that we really are concerned with: pressure. Okay, pressure is force per unit area. We will, in this course, deal exclusively with absolute pressure. So that's going to be the gauge pressure plus the atmospheric pressure, and that combines to absolute pressure. Now, we typically are going to just say, it's 1 atmosphere is the atmospheric pressure. That's equivalent to 101.3 kilopascals or 1.013 bars or 14.696 psia. Now, a psia is a pound per square inch absolute, or pound force over inch squared if you're trying to do it with unit conversions. Temperature, you guys know temperature in degrees Fahrenheit, temperature in Celsius. We also then have a couple of other things. Absolute temperature is one, and then also there's something called the 0th law of thermodynamics. So let's first talk about this 0th law of thermodynamics. It's the 0th law because it's so fundamental to everything else in the course. So therefore you sort of just need to accept that this is true. Fortunately, I call this the mom thermometer. Okay? the zeroth law is stated as, if two bodies have equality of temperature with a third body, then they have equality of temperature with each other. Okay, so why is this the mom thermometer? Oh, I'm sick. Mom comes up, puts her hand on her forehead, puts her hand on your forehead, and she says, you're not sick, go to school. Right? Okay, so what she's doing is she's saying, third body, this body is equal, your body is equal, therefore those two have the same temperature. Now what Mom didn't account for is that she was sick, right? The other thing we need is we're going to need to be able to work with temperature in absolute. Okay, equations of state, which are sort of the lifeblood for chemical engineers, are all based on absolute temperatures. The absolute temperature scale for SI is kelvins. So we're going to take our temperature in degrees C and add 273.15. For the American Engineering or English units, we're going to work with degrees Fahrenheit is our relative temperature scale. And to get it to Rankine, which is the absolute scale, you add 459.67. Now both kelvins and Rankines are always positive. Temperature is not defined as negative on an absolute scale. Other conversion formulas are shown below for temperatures from C to Fahrenheit or Kelvin to Rankine. One last topic for this video is energy. Again, you should have probably had your physics course by now, okay? So, there are three forms of energy: internal energy, kinetic energy, and potential energy. Okay? Potential energy is the stored energy. We usually equate it to height. You can also have potential energy due to some other things like magnetism and so forth. But mgz, or the height, okay, is going to be that potential energy. Kinetic energy is an active energy, so it's 1/2 mv squared. Okay? It's very difficult because Microsoft Word does not wish me to put little arrows over the V's unless I use equation editor. So therefore, you're going to have to definitely, whenever you see a V, just check the units. You're not going to really know, is that a total volume, is that an intensive volume, volume per mass, volume per mole, or is that a velocity? So whenever you see a V, just really take a moment and check the units and make sure you know what it is. Now, total energy is just simply the sum of those three forms of energy. If you want to divide through everything by mass or by moles, you can get it into the intensive total energy, which would be little u plus ke plus pe, or 1/2 v squared, and gz is your kinetic and potential energy term. The units on this, typically we use SI units, use kilojoules, and English units will use BTUs for energy. So we're going to pause the video here, and when we come back, we're going to be looking at phases and the data tables.